Question 1. The solubility of barium nitrate at 60 degrees Celsius is 20 grams per 100 grams of solution, and at 100 degrees Celsius is 32 grams per 100 grams of solution. What mass of BaNO32 crystals will form if 300 grams of a saturated aqueous solution of barium nitrate is cooled from 100 degrees Celsius to 60 degrees Celsius? Now we need to note that we're now using 300 grams of the solution and we're not using 100 grams of solution, so we need to do cross multiplication. So for the 300 grams, so now we know that 20 grams of the barium nitrate will dissolve in 100 grams of solution at temperature of 60 degrees Celsius. And for the 100 degrees Celsius, we're going to have 32 grams of BaNO32 in 100 grams of solution. Now for 300 grams of solution, we need to do cross multiplication, and the amount of barium nitrate that we're going to have for 300 grams of solution is going to be 60 grams, and over here we're going to have, at 100 degrees Celsius, we're going to have 96 grams. So if we cool the solution from 100 degrees Celsius to 60 degrees Celsius, then we need to subtract these values, the 96 and 60, and so we're going to get an answer of 36. So the answer is going to be 36 grams of barium nitrate crystals will form. Question 2. Write the net ionic equation that takes place when a solution of CaNO32, which is calcium nitrate, is mixed with a solution of Na2CO3, which is sodium carbonate. Now, the net ionic equation stands for the equation in which I show only the chemical species that participate in the reaction and they form the precipitate. So only the species that participate in the reaction, we are going to use them to write the net ionic equation. So first I have CaNO32 that's reacting with Na2CO3. Now when these mix, we're going to form, the ions are going to be Ca2 plus NO3 minus, and then we're going to have Na plus and CO32 minus. Now these are going to mix together and these are going to mix together, and we're going to have NaNO3 and CaCO3. However, everything with alkali metal ions or with nitrate ions is soluble, so these are not going to form the precipitate. They're not going to be part of the net ionic equation. However, Ca2 plus and CO32 minus, they are going to form precipitate, as a carbonate ion is only soluble with group 1 ions and with the ammonium ion, which is NH4 plus. So the precipitate that's going to form is CaCO3, and the net ionic equation is going to be Ca2 plus aqueous plus CO3 2 minus aqueous. They will react to form CaCO3 solid. Now what's the color of the precipitate? Now CaCO3 is calcium carbonate, and it's actually the main component of chalk, and it is a white precipitate. So this is a white precipitate. The name of the precipitate, we have calcium and we have carbonate, so it's calcium carbonate. So this is the answer for the first part. This is the net ionic equation with the state symbol. The color of the precipitate is going to be white, and the name of the precipitate will be calcium carbonate. Question 3. Solution is known to contain lead nitrate, PbNO32, and BaNO32. Which of the following is added to remove the lead ions from the solution without removing the barium ions? Now, another way I can read this question is I have the Pb2 plus ion in the solution. I also have NO3 minus present, and I also have the Ba2 plus. Now I want something that will form a precipitate with Pb2 plus in order to remove it as a solid, where it's going to stick on the filter paper, whereas the solution is going to go down. So if we have, let's say, filter paper, the solid will stick on the filter paper, and we're going to have the Ba2 plus as the filtrate. So I want something that will form a precipitate with Pb2 plus, and something that will not form a precipitate, so no precipitate with Ba2 plus. So let us check each option that we have over here and see if it's correct or not. Now for HNO3, we're going to have the H plus, and we're going to have NO3 minus. Now, I want you to only look at the anion as Pb2 plus, which is a cation, is going to react with the anion and not with the cation. So in all of these options, I want to focus on the anions that are present, because they are the ones that might form a precipitate with either these two cations. So for the first one, we have the nitrate, and nitrate is soluble with everything. We already have also nitrate over here. So since nitrate is soluble with Pb2 plus and Ba2 plus, we cannot remove the Pb2 plus. So this is wrong. Now for sulfate, we're going to focus on the SO42 minus, and SO42 minus forms a precipitate with both, since SO42 minus is insoluble with the Castro-Bard group, which include the Ba2 plus and the Pb2 plus. So since it is insoluble with Pb2 plus, it will form a precipitate with Pb2 plus, and it will also form a precipitate with Ba2 plus. So both are insoluble, so I cannot separate them in this case, because I need only one of the ion, which is the Pb2 plus, to be insoluble. Now if I go to Na2CO3, now CO3 2 minus is insoluble with both ions also. So I cannot use Na2CO3. If I go to Br minus, so Br minus is insoluble with LCS, and L stands for Pb2 plus. However, Br minus is soluble with Ba2 plus. So since it's soluble with Ba2 plus and insoluble with the Pb2 plus, the only correct option is NaBr. Question 4. The saturated solution of iron 3 hydroxide has a solubility of 2.1 times 10 to the power minus 10 m. They are asking to calculate the solubility product, which is Ksp, of iron hydroxide, and give your answer in scientific notation to 3 significant figures. So I'm going directly to set an ice table. I'm going to write the equation first. So we have FeOH3. The ions present are Fe3 plus. As you can see, we have this subscript, this 3 over here. And Fe usually has either a 2 plus, or it could be Fe3 plus. But since the subscript is 3, so it's Fe3 plus. And OH is the hydroxide ion, which has a charge of, which is OH minus, of -1. So first I'm going to write the reaction. FeOH3, which is a solid, is going to give Fe3 plus aqueous plus 3 OH minus aqueous. I'm going to use an ice table. Now, since this is a solid, I'm going to cancel. I'm not going to work on this part. And for Fe3 plus, it's going to be 0. And here we're going to have also 0. Then the change is going to be over here plus X. Of course, the reaction is going to give ions, so it's going to be plus. And we are going to have over here plus 3X. Now we have X and 3X. And now I can use the Ksp. I'm going to write the Ksp expression. So for the Ksp, the Ksp is going to be equal to Fe3 plus multiplied by OH minus to the power of 3. And I place power of 3 since I have the coefficient over here, which is 3. And now we're going to substitute by X. Fe3 plus is X, and OH minus is 3X to the power of 3. So we're going to get 27X to the power of 4. And X is given as solubility. Solubility stands for concentration, and it is 2.1 times 10 to the power minus 10. So I'm going to put 27 times 2.1 times 10 to the power of minus 10 to the power of 4, and the answer is going to be equal to 5.25 times 10 to the power minus 38. So this is the final answer, and it is to 3 significant figures. Question 5. A sample of 400 milliliter of 0.004 m PbNO32, which is lead nitrate solution, is mixed with a sample of 100 milliliter of 0.005 m KBr potassium bromide. The following chemical equation represents the reaction that took place at a temperature T. And we have the KSP value, and this is the reaction, or this actually the, if I want to say, the dissociation equation. And they asked us to calculate Q, assuming the volumes are additive, and determine if a precipitate will form. Now, first, if they did not give us this equation, we need to know the precipitate that's going to form from this question. So we have Pb NO32, and it is being mixed by KBr. So the ions are Pb2 plus, NO3 minus, K plus, and Br minus. Now, everything with a nitrate, which is, or the alkali metal ion, which is K plus, is going to be soluble, and they're not going to form a precipitate. However, Br minus is insoluble with LCS, and L is the Pb2 plus. So Pb2 plus and Br minus are insoluble. So first I'm going to find the value for Q, and to find the value of Q we need to use the mass action expression. So Q is going to be equal to Pb2 plus multiplied by Br minus to the power of 2. And remember, we need to raise it to the power of 2 since we have 2 over here. And we're not going to include the solid, as solid is not incorporated in the Q, or neither in the KSP. Now I need to find the concentration for Pb2 plus and Br minus after we mix the two solutions together. So the concentration of Pb2 plus, I'm going to use this formula. C nu is equal to N old over V total, or I'm going to write C old times the V old. So I mean old volume times the old concentration over the total volume. Now for Pb2 plus, we are going to have the old concentration is actually, so Pb2 plus comes from lead nitrate. So I need to look at these values and not at these values since we have Pb2 plus. So the volume is going to be changed to liter. It's going to be 0.4 multiplied by the old concentration and divided by the V total. Now V total is equal to 500 milliliter because we have 400 from this solution and 100 from this solution. So it's going to be equal to 0.5. So let's multiply for the Pb2 plus, it's going to be 0.004. This is the concentration multiplied by the volume, which is the old volume 400, and I change it to liter, divided by 0.5, multiplied by the Br minus, which is 0.005 multiplied by 0.1 over 0.5 raised to the power of 2. And all of it should be raised to the power of 2. And the final answer will be 3.2 times 10 to the power of minus 9. So I found the value for Q. Now I need to determine if a precipitate will form. So I need to compare the values of KSP, which is 6.6 times 10 to the power minus 6, and the value of Q. Now Q is definitely less than KSP, so no precipitate will form. Question 6. Find the weight of the precipitate formed when 250 milliliter of 0.5 m NaBr is added to 25 milliliter of 0.1 m silver nitrate, which is AgNO3. Here I have the atomic masses, and they said give your answer to 3 significant figures. Now, to solve this question, I need to write first the equation that's taking place. And the equation that is taking place is NaBr is reacting with the AgNO3, and they're going to give the product, which are AgBr and NaNO3. Now, one of these are insoluble. One of the products are insoluble, and we need to refer back to the solubility rules. And I determined the products by first writing the ion. So I have Na plus, Br minus, the bromide ion, Ag plus, and I also have the nitrate ion, which is NO3 minus. So Na plus and NO3 minus are going to form NaNO3. Ag plus and Br minus are going to form the AgBr. So of course these are going to be soluble, they are the reactants, and of course we know everything with nitrate, everything with the alkali metal ion is soluble. NaNO3 is definitely soluble because we have an alkali metal ion and nitrate. Now AgBr, Br minus is actually insoluble with LCS, and S stands for the silver, which is the Ag+. So this is the precipitate that will form. Now, the next step that I need to do is to find the number of moles for the reactants and determine which one of them is the limiting by also finding the reaction ratio. So let's start by finding the number of moles. Now, the number of moles for NABR is equal to the concentration multiplied by the volume, and the concentration is 0.5, and it's going to be multiplied by the volume, which is 0.25, because we're going to change it to liter. So we're going to have 0.25 multiplied by 0.5, and we're going to have an answer of 0.125 mole. For the number of moles of AgNO3, we're going to do C times V. Now, AgNO3 has a concentration of 0.1 and volume of 0.025. So it's going to be 0.1 multiplied by 0.025, and we're going to have the number of moles equal to 2.5 times 10 to the power of minus 3 moles. Now, I need to determine which one of them is the limiting. So the coefficient in this case is 1, and here we have a coefficient of 1. So let's determine the reaction ratio. Now the reaction ratio is equal to the number of moles that I found over the coefficient in the balanced equation. Now the coefficient in the balanced equation is 1, so it's not going to affect the number of moles that I found. So in both cases, I'm going to have the reaction ratio for the NABR equal to 0.125. The reaction ratio for AgNO3 is going to be equal to 2.5 times 10 to the power minus 3. And so we have the reaction ratio for AgNO3 is less, so AgNO3 is going to be the limiting reactant. And the limiting reactant is the one that's going to tell me how much products I'm going to have. So if I write the reaction again, NABR plus AgNO3, they react to give AgBr plus NaNO3. For every 1 mole of this limiting reactant, I'm going to form 1 mole of AgBr. Now I have the number of moles that I actually have are 2.5 times 10 to the power minus 3, which I got over here. And I'm going to do cross multiplication, so it's going to be, of course, the same, 2.5 times 10 to the power minus 3 moles for the AgBr. Now, since I have the actual number of moles, I can do N is equal to mass over molar mass. And the mass is going to be equal to N times the molar mass. So let's erase this part. So mass is equal N times the molar mass. The number of moles is 2.5 times 10 to the power of minus 3, which is this value over here. And I'm going to multiply by the molar mass of AgBr, which is actually going to be equal to 108 plus, so it's going to be equal to 108 plus the Br, which is 80. And we're going to get a value of 188. Therefore, the mass is going to be equal to 2.5 times 10 to the power of minus 3 times 188, and we're going to get a value of 0.470 grams. And we need to include this 0 over here because they need the answer to 3 significant figures. Question 7. 0.004 moles of HCl and 1 times 10 to the power minus 6 mole of PbNO32 are mixed, forming a 2-liter solution. Write the dissociation equation for the formed precipitate. So first I need to determine what precipitate is going to form. So I have HCl plus PbNO32, and the ions are H plus, Cl minus, Pb2 plus, and NO3 minus. Now, if I mix H plus and NO3 minus, no precipitate will form because everything is soluble with NO3 minus. So HNO3 is soluble. However, Cl minus, so let's first write the product. So I will have HNO3 plus PbCl2, and the reaction is not balanced, so I have to put 2 over here and 2 over here, but there's no need to balance the equation because they're only asking us about the precipitate. So this is soluble. However, the PbCl2, which is Pb2 plus, and Cl minus is insoluble. And this is because Cl minus is insoluble with LCS, where L stands for the lead, which is Pb2 plus. So the dissociation equation will be for PbCl2, and a dissociation equation goes from a solid to the ions that are formed. So we're going to have PbCl2 solid. They will give, and we need to include the arrows. To show it's a reversible reaction. We're going to have Pb2 plus aqueous plus Cl minus, and we need to write 2 over here before the Cl minus. Now the last question was calculate Q, which is the mass action value. So Q is going to be equal to Pb2 plus multiplied by Cl minus to the power of 2. Now for Pb2 plus, I'm going to also use the formula C nu equal N old over V total. Since they gave me over here the number of moles, now Pb2 plus, the source of Pb2 plus is PbNO32, which has the number of moles of 1 times 10 to the power minus 6, and a V total of 2 liters of solution. So Pb2 plus, I'm going to substitute N by 1 times 10 power minus 6 over 2 multiplied by the number of moles for Cl minus, which comes from HCl, which is 0.004 mole. So I'm going to put 0.004 0 to the divided by 2, which is the total volume, to the power of 2. The answer will be 2 times 10 to the power of minus 12, and this is the value for Q. Now the last question was determine if a precipitate will form or not, given that KSP is 1.3 times 10 to the power minus 8. So Q is less than KSP, so no precipitate will form. Question 8. Calculate the KSP of PbCl2 knowing that it has a solubility of 1.1 times 10 minus 2 at a specific temperature in water. So let's start with the first one. So we need the KSP, and remember that when they give you the solubility, it's as if they gave you the X, which is in the ice table. So let's first write the reaction. PbCl2 will produce Pb2 plus aqueous plus 2Cl minus. This is the dissociation equation. I'm going to use an ICE table. So since it's a solid, I'm going to ignore this part. I'm going to put 0 over here, 0 over here, because we don't have ions at the beginning. The ions are going to increase, so we're going to have plus X plus 2X, X over here and 2X over here. And then we know that X is equal to 1.1 times 10 to the power of minus 2. So KSP is equal to Pb2 plus multiplied by Cl minus squared, and it's going to be X because we're going to substitute by this these values over here, the X, and multiplied by 2X squared, which will be 4X power 3. And if I substitute X by this value, I'm going to get a KSP of 5.3 times 10 to the power of minus 6. So this is the value for KSP. Now for the next question, I have to calculate the solubility. So now I have to find X, and I'm given the KSP. I'm going to use the same way. I'm going to write the equation CuCl, and it's going to give Cu plus Cl minus. Now I did not put over here Cu2 plus because, as you can see, there's no coefficient over here. If it was CuCl2, then it would be Cu2 plus. But over here we don't have a subscript, over here. So it's not going to be Cu2 plus because we don't have a 2 over here. And I'm going to use an ICE table. This is a solid. These are aqueous. Ignore this part, 0, 0, plus X, X, and X. KSP is going to be equal to X squared. Therefore, x is going to be equal to radical of KSP, which is equal to, now the KSP is given as 3.2 times 10 to the power of minus 7. So I'm going to do radical of 3.2 times 10 power minus 7. And the answer is going to be 5.7 times 10 to the power of minus 4. This is the x that I'm going to get, which is the concentration. Question 9. 300 milliliters of 0.2 m magnesium nitrate are added to 200 milliliters of 0.2 m sodium hydroxide, NaOH. KSP of MgOH2 is 1.8 times 10 to the power minus 11. And they said to calculate the concentration of Mg2 plus and OH minus in the solution and give your answers to three significant figures. Now, first, let's say I do not have the value for KSP, and or let's say I have the value of KSP, but I do not have the precipitate that is formed. So they did not tell me that the KSP is for MgOH2. So in order to determine the precipitate, I have to first find out the product. So where we have magnesium nitrate reacting with NaOH, the ions are Mg2 plus and NO3 minus. I have Na plus and OH minus. Now, Mg2 plus is going to react with the OH minus and Na plus with NO3 minus, and we're going to have MgOH2 plus NaNO3. So without balancing, we can, there's no need to balance. I just want to know the precipitate that's formed in this case. So it's not going to be NaNO3 since NO3 minus is soluble with everything, and Na plus is also soluble with everything since it is an alkali metal ion. However, MgOH2, OH minus is insoluble with the Mg2 plus, as usually OH minus is soluble with the alkali ions of group 1 and NH4 plus. So this is going to be the precipitate, which is MgOH2. So now let's go for the first question, which is to calculate the concentration of Mg2 plus and OH minus in the solution. So it's as if after we mix the two solution, and give your answer to three significant figures. Now the concentration for Mg2 plus is going to be equal to, we're going to use the formula, which is C nu is equal to N old over V total, where we have the old concentration multiplied by the old volume over the total volume. Now Mg2 plus has the, so I'm directly going to substitute the values. Mg2 plus has a concentration of 0.2, and I'm going to change the volume to liters, so it's going to be 0.3, and I'm going to divide by the total volume. Now V total is equal to 200 plus 300, so I'm going to have 500 milliliters, so it's 0.5 liter. Divide by 0.5, I'm going to get the concentration as 0.12 m after mixing. Now for OH minus, I'm going to do the same thing, and I'm going to do the concentration of OH minus is 0.2, and I'm going to multiply it by 0.2 because I have the volume is 200, changing it to liter, and the total volume is 0.5. So OH minus is going to be equal to 0.08 m. Now, since they said give your answer to three significant figures, so I have to put over here 0.120, and over here I have to put 0.0800 m, and now I have three significant figure in each answer. Now for part B, they said calculate the reaction quotient, the mass action expression. We need to use the mass action expression and give your answer in scientific notation to three significant figures. So Q is equal to, first of all, let's write the reaction that's taking place. So MgOH2, which is the precipitate. I'm going to write the dissociation for the precipitate, and it's going to be Mg2 plus 2OH minus. So Q is going to be equal to Mg2 plus multiplied by OH minus to the power of 2. I will use the values that I got for the first part, which are 0.12 and 0.08. So I'm going to have 0.120 multiplied by 0.08 squared, and Q is going to be equal to 7.68 times 10 to the power minus 4. So I have three significant figures. and this is the value for Q. Now for the final part, they said determine whether a precipitate will form or not. So I have to compare the Q value that I got over here with the KSP that's given, which is 1.8 times 10 to the power minus 11. As you can see that Q is much larger than the KSP, so Q is greater than KSP, so a precipitate will form.